So this is the first problem of today's Codechef Division 2. And in this problem, we are given that we have n boys and pairs, n boys and girls, out of which x are the number of boys and the remaining are girls. Now, in this problem, they'll first form exactly like k groups, as many groups as they can, and then they will, like the remaining, can dance in pairs, and all the people that are left will read the book. So this is a very simple problem. See, initially we have n boys and girls. So let's say this is boys and girls. Then we have x as number of boys. So there are n minus x girls. So first of all, out of this, they'll keep like all the boys and all the girls. They'll try to form as many k groups as possible, which are of k boys or k girls. So how many will be left? Here x plus mod k, and from here we'll get n minus x mod k, right? Out of these, let's say this is A, this is B. So whichever is minimum, that many pairs can be formed. So our answer is nothing but maximum of AB minus minimum of AB. Is anyone having any doubt in this? I have just like these many pairs can be formed. Let's say this is 5, this is 3. So we'll be able to form 3 pairs, 3 boys, 3 girls, and remaining 2 will be left. They'll have to read book. Is it clear?
Yes.
So let me show you the implementation. So this is the implementation. I have first taken n as input, n, x, and k as input. Then this is the number of girls. I have directly subtracted x from n. So this is the number of girls left after groups are formed, and this is the number of boys that are left after the groups are formed. So this is maximum of n comma x minus minimum of n comma x. Nobody is having any doubt in this, right?
No.
Okay, so let's go to the next problem. So in the next problem, we're given that we have like chef has A marbles and his friend has B marbles. Now they want to redistribute these marbles among themselves such that after redistributing, and his friend both have at least one marble each, and the number of marbles with chef is divisible by the number of marbles with his friend. So we have to find the minimum number of marbles that need to be transferred from one person to the another person to achieve this. So the only thing that was like to observe in this problem is the constraints. Like this is what makes this problem easy. There are 10 to the power 3, 1,000 test cases, and A and B are also up to 1,000. So see, the problem is that we have A marbles with chef and B marbles with his friend. Let me and B marbles with his friend. Now, what happens? See, there can be like how many transactions do we want? Like how many plus minus x marbles do we need to add here? How many plus minus x marbles do we need to, like if we are adding here, we'll subtract here, and if we are subtracting here, we'll add here from here, such that A modulo B is equals to 0, right? This is what we have to do, and we have to find minimum value of x for which this is true. Now, first of all, if we first look at this, that will increase x and will decrease from b, like will increase from in A and will decrease in B. So we can simply just do brute force. That is while A plus x modulo B minus x is not equals to 0, we'll keep doing this x plus plus. It's guaranteed that after some iterations, we'll always get this condition terminated. Why? Because this is nothing but A plus x divisible by B minus x. So after some iterations, B minus x will become 1. This is division. This is modulo. So B minus x, once this value becomes 1, this loop will get terminated and you'll get some x. That x is nothing but what is the value that you have to subtract from B and what is the value that you have to add to A, such that A plus x becomes divisible by B minus x. Now you'll have to also look the other way around. When you are subtracting something from A, and you're adding something to B, right? Because it, like, we are not restricted. Like in the problem statement, we have no restrictions like we have to take from his friend only and we have to add in chef only. There are no such kind of restrictions mentioned, right? So let's try it the other way around. Now we need to check while a minus x modulo b plus x is not equals to 0. While this is not true, we'll keep incrementing x plus plus. Now, along with this, we can leave here. What will happen? Eventually, we'll get, let's say this is x dash, x dash, x dash. Once like x dash becomes equals to a, x dash becomes equals to a, this will also get terminated because this thing will become 0, right? So instead, like we can do like this also, do this and then finally check if x dash is 0, then don't take this. Otherwise, take minimum of x and x dash. Like if x dash is a, if x dash is a, then you don't have to consider this, right? Because in the problem statement, it's mentioned that both should have at least one marble, right? Yes, no.
Yes.
Yeah,
Other
for the
like, yes,
for
yes,
the
yes.
upper case also we have to take now b minus x1.
No, no, no. As I said, x will never be equals to b because when x is less than b, when like we'll start from x equals to 0. When x is equals to b minus 1, this condition will get terminated. Why? Because this thing will become 1. 1 divides everything. 1 will divide this thing, right?
But
Like this is the condition that this thing is not equals to 0. So this thing will become 0 when x becomes b minus 1 because this thing will become 1. So x will never be equals to b. We'll start from 0 and before reaching x, because if anyway, if x becomes b, then this thing is not defined. Like what is something modulo 0? Nothing, right? This is not defined. So x will never be equals to b for the first condition. For the second, it can be equals to a and you don't have to consider it. Otherwise, you can also have second kind of like, you can have a second check here that x is less than a or x is less than a minus 1. So, and finally, you can check for some x dash, like x dash is less than equals to a minus 1, whether the value that you get is valid or not. Like you can do it like in any way, either put an extra condition here and then later check, otherwise do just this thing. Finally, what is the time complexity of this? See how many iterations of x we are having. At maximum of a and b, right? So 1,000 times 1,000, like at max 1,000 iterations for each test case, and there are 10 to the power 3 test cases, so 10 to the power 6. This will pass the given time limit, the given test time constraint. Is it clear? Like this is just plain brute force. So is there any doubt? Yes, no, anything?
No.
Okay.
yeah,
So yes, yes, yes.
for example, if that number of test cases is like 10 raised to power 4, so how do you approach this question?
Like for 10 to the power 4 also it will pass. Like you'll have 10 to the power 7. If it is really high, then this problem will become like if you have around 10 to the power maybe 6 test cases and A and B are also going up till maybe 10 to the power 9 or 10 to the power 12, then this will become a different problem. Then it's like you won't be able to apply brute force. So like what we can do, like probably you can like maybe if you want, like I'll discuss this with you after the session because I also don't have a solution for that right now. I'll have to think and I don't like want to discuss this right now between this session. Okay.
Okay.
So let me show you the implementation. So this is the implementation. First, I have taken A and B as input. Then I have taken like while b minus x is, I don't have to do this, but since I just copy pasted, like once I wrote this, I just copied it and pasted it here. I have written this. You don't have to do this. It will like automatically work for this first condition. So while this is not equal to 0, I keep increasing x. This is the second. In like while explaining, I wrote this as x dash. I have written this as y here. So I have included this condition here, so that's why I'm checking it later. Like otherwise, you could have just checked if this value is equals to like y is equals to a, then you could have just ignored it, but I'm doing it like this. So my y will never be equals to a because of this condition. So that's why I'm checking this thing here. If this is not true, if this is like not divisible, this will give you some value more than 0. So that's why y will become 1e9. So I have printing minimum of x and y. So hopefully this is clear, right? Yes, no.
Yes.
Okay. So let's go to the next problem. So in the next problem, we're given that Ben is fighting monsters with a health of H. So Ben is fighting a monster with a health of H, and he starts with an attack power of 1. Now Ben has two types of moves. He can use a regular attack, which damages the monster by his current attack power. And after this, his attack power doubles. Or he can use a special move, choose a prime number P, which is less than or equals to H, H being the current health of the monster, and deal P damage to the monster. Now, this move can also be done at most once. Not also, like this move can be done any number of times. This move can be only done at most once. So after the second move, Ben's attack power doesn't get doubled. So we have to find the minimum number of moves required to kill the monster. And in order to kill the monster, Ben must deal exactly H damage to it. Not more than H, not less than H, exactly H. So we have to find the minimum number of moves needed for Ben to kill the monster, or print -1. So these are the number of tests, and this is the health. So see, health is less than or equals to 1,000,000, 10 to the power 6, right? So first of all, see how to solve this problem. See what we can do. We'll iterate in, see, initially, let's say the power is H. So if H is a prime, let's say if H is prime, let's say there's a function is prime, and this value is a prime, what is our answer? Our answer will be simply 1, right? In one move, we can kill this monster. Why? Because we can just deal this much damage to the monster. Because there is a prime which is actually equals to H, which is less than equals to H. There is this prime H itself, right? Otherwise, the current power is, we don't have any other option. The current power is 1. We'll have to do H minus 1. We'll have to deal this much damage. We cannot, we like, why, you might think, why not take any other, like any other prime? Why I'm taking just H? Because if there is, let's say there is some prime P dash, which is less than H, and that is optimal, it will still be left. Why? Because see, the 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 attacks that we are performing on the first type are of this kind. First, we'll deal a damage of 1, then we will deal a damage of 2, then 4, then 8, then 16, and like this. So after each of these, we can check if the value remaining is a prime. If it is a prime, then the answer is yes. Otherwise, if we keep doing this and our value becomes 0, then also our answer is yes, because the second type of damage can be performed at max, once. It doesn't mean that we have to perform it. We can perform it or we cannot perform, like, or we don't perform it. But if while doing this, like these kinds of subtractions from our H, the value becomes negative, then the answer is not possible. Like, how can you get the answer, right? Right? So what we have to do, just iterate in these values, 1, 2, 4, like 2 to the powers, and keep subtracting these values from H minus 2, then the value is, let's say, H dash, so H dash minus 4, and if after some iterations you get a value which is prime, the answer is, like, these are the minimum number of operations. Otherwise, the answer is -1. Why can't we first subtract maximum possible prime? See, it won't matter. If there is a prime, which you'll see, even if you subtract some prime, like in each iteration we are checking, right? Are we getting a prime or not? See, let's see, if you subtracted some prime, which is 16, what is the biggest prime that is coming to your mind? Let's say 53. 53 is a prime, right? Yes, I think it's a prime. 53. 51 is also a prime. Anyway, let's take 53. So let's say 53 plus 16. What is this? 9, 5, 6, 69. So let's say you got 69. Now you might be thinking, if you're like, if in the start we took 53 and then we followed 2 to the powers, you'll get optimal answer. Otherwise, if we follow this, we might subtract 16 and then we might also subtract 32, but this won't happen. I'm checking after each subtraction whether the remaining thing is a prime or not. If it is not a prime, anyway, you'll have to do some operation. See, at the start we had 69. Is it a prime? No. So you'll have to subtract 1 from this, either now or either later on. Even if you subtracted prime from this, you will be left with something, right? There will be something, and from that you'll subtract 1. The current power is 1. You'll have to subtract 1. So why not first subtract 1? Like, how does it matter, right? If this is not a prime, you'll have to subtract this 1 from it. Like, whatever the current power is, if this value is not a prime, you'll have to subtract this current power once. So first subtract it and then check whether it's a prime or not. If it is a prime, then you have got your minimum number of moves. Otherwise, you'll have to subtract this. Why? Because this is not a prime, right? You cannot do the second kind of operation. Like, if, okay, even if this is not a prime and you subtracted from this a prime, like, I know, okay, you might be confused that, okay, even if this is not a prime, we can take any prime which is less than or equals to h. So I'm always taking this equals to. Why not taking less than? So you might be thinking, if this is 69, why not take the biggest prime? And I'm saying it doesn't matter. If the current power is this current, if you took the prime, and I already have told you that this is not a prime. So any prime that you'll take will be less than 69, not equals to 69, right? So there will be something left. 69 minus prime. This thing will be left, right? So on that thing also, you'll have to subtract the current power. Like, from that, let's say 69 minus prime is x. So you'll have to do x minus current, right? You'll have to do this thing. X is more than 0. Why is x more than 0? Because 69 is more than prime. Is it making sense now? We'll have to subtract this current power either now or later on. Okay, so is this clear to everyone? Yes, no. Let's take one example, like one sample test case. So let's take, so from 10, if let's say we start from 10, first, is 10 a prime? No, it's not. So we'll have to subtract 1. So let's subtract 1, we'll get 9. Is 9 a prime? No. So we'll have to subtract 2. Subtract 2. 7. Is 7 a prime? Yes, 7 is a prime. So our answer is 3 operations. We could have done like 10 if you start with subtracting 7. So you'll get 3. You'll get 3. And if you get 3, you'll have to subtract, like, you have used your second type of operation, right? If you have used your second type of operation, now you can use only first type of operation. And your current power, attack power is 1. So if you start from 3, you'll have to subtract 1, you'll get 2, and then your current power will become 2, and you'll subtract 2. So 2 minus 2 is 0. You can look at it at like this also, like you start from subtracting 7, but the better way is you have to, if 10 is not a prime, you'll subtract, even if you choose any prime which is less than 10, you'll be left with something. So you'll have to subtract 1. If 9 is not a prime, you'll have to subtract the current power, which is 2. Now you're left with a prime. Is it clear? Like, I think I have explained it enough. Like, how can a minimum move involve smaller prime? It's not possible. See, let's say x, you get x in input. You are saying instead of p, which is the largest prime, you are taking some smaller prime, which is p dash. So if the number which was left without the biggest prime is x minus p, and the number which is left without, like with this is p dash is less than p. This is a smaller prime. This is bigger, right? This is bigger. And this is smaller. This value is smaller because p is more than p dash. Now tell me one thing. If in both of these, I have to make these numbers 0 by using only this thing. first do -1, then do -2, then do -4, then do -8. So if this is a smaller number, I'll have to do less operations here and more, like the operations will be same only, right? I can do -4, -8, -16. So here I'll have to do more operations. Is it clear? Now another query is, what if I took, like, I'm checking each time if the remaining thing is a prime, then I'll remove it. So if the answer is possible, I'll get it that way. Otherwise, if the answer is not possible, then I won't get it. Like after, like, I subtracted 1, I'll follow this path only. The only thing is you'll follow this path. Like you'll first remove -1, then -2, -4, -6. After these will be some operations, and optional is P. The thing is, you'll have to follow this. So if the start is not prime, you cannot directly jump to this, subtract -1. Again, check. If this is not a prime, again, you'll have to subtract -2, right? If the answer is possible, you'll get it that way. Yes, you can't get answer. Like, first of all, you won't get optimal answer. Like if you're getting answer by subtracting the biggest prime, but let's say you had H and you initially get this in input, and you're not getting answer by subtracting the biggest prime, then also from this solution also you won't get that answer. You'll get the biggest prime which can be subtracted, like from which you'll get the optimal answer. Okay. Is it clear? Yes, no? Okay. Let me show you the implementation. So, okay, there is one thing, like how to get the primes. Since the number is up till only 10 to the power 6, we can easily use sieve-like method to get the we can use sieve-like method to get whether the ith number is prime or not. So what we can do, we can initially make is prime vector, and it will be 1 if the ith number is prime. And we can simply follow for every prime, we can go from 2 to the power I, 2 into I, till whatever the limit is. In this case, 10 to the power 6. And each time we'll start from this, we'll go up till this, and we can each time iterate over all the multiples of I, and we can mark them as not prime. So this is a simple sieve-like method. Like, why do we need this? So that later on we'll be easily able to find whether some number is a prime or not. So let me show you the implementation. So this is the implementation in this. First, this is the is prime vector, and everything from 2 to n is prime. Then if the current number is not prime, I'll simply continue. Otherwise, if the ith number is prime, all of its multiples will be not prime. Later on, this is my current power. This is the answer. And while n is 0, that means I have some power left. Like the monster has some power left. I'm first increasing the number of operations that I'll do. If this number is prime, simply make this 0. Why make this 0? Because I can subtract, I can deal this much damage, exactly this much damage. So n will become 0 and break this loop. Otherwise, if this is not a prime, subtract current from n, that is current power, and multiply the current power by 2. Finally, we can check if n is exactly 0, we can print our answer. Otherwise, we can print -1. Is it clear? Like, whatever doubt you are having, like, I think it's clear. But if you're having doubt, why, like, why is it always optimal to take like this way? Like, we are not taking directly the biggest prime. We are always subtracting, and if the prime that we are getting, like, it's not always the same. Like if you have 10, like in 10, the biggest prime is 7. Okay, like we are not directly taking the smallest prime, which is less than h. We are subtracting 1, 2, 4 in this order, and then if after some operations we are getting some number which is fine, then we are taking it. Okay. So let's go to the next problem. So in this problem, we have this is done this. So in this problem, we have Chef and Shafina are playing a game of Tetris together, and in a single move, a player can either clear 1, 2, 3, or 4 lines of blocks, and clearing 4 lines in a single move is called Tetris. Now, Chef and Shafina take turns playing, with the chef starting first, and whenever the current player clears only one line, the turn shifts to the other player. Otherwise, it remains with the current player, and they will stop playing as soon as at least L lines are cleared in total. Now, that is, the game stops when the sum of total lines removed by both the players is at least L. So, Chef wants to end this game in style, and he would like to be the one who finishes the game and do so getting a Tetris, that is clearing 4 lines. So how many sequence of moves are there in which this can happen? And we have to print it modulo 10 to the power 9 plus 7. So first of all, let's say this is, see, if chef does one move, this like, who has the control at this line? Shafina, right? And now Shafina can either remove 1, 2, 3, or 4. Same way, who has the control here? Chef has the control here, right? And he can either remove 1, 2, 3, or 4. So this is a very simple problem. It's a very standard DP problem. Like what you can do, let's make two arrays, x and y. X of I will give me how many number of ways there are such that ith, like everything before this is removed, this is I, and chef has the control. Like chef is having the move and we are at this thing. Everything before this is removed. And y of I will give me everything before I is removed, and Shafina is having the move. So first tell me what is x1 and y1. What is x1? If everything before this is removed and chef is having a move, how many number of ways are there for chef? Like who is starting the game? Chef is starting the game. So this is 1 and this is 0. Is there any doubt?
No.
Okay. Now for everything from, let's say, from 1 to n, what we can do from 1 to n, like like we have some queries to answer it. We have 10 to the power 6, 10 to the power 5 test cases to answer, and L will be from 1 to 10 to the power 5. So if L is from 1 to 10 to the power 5, we'll go from 1 to 10 to the power 5. And what we can do, see, if look at this only. If chef was here, if chef did remove this at I plus 1, who will have the move? Shafina, right? Shafina will have. Otherwise, at I plus 2, I plus 3, and I plus 4. If chef removed 2, if chef removed 3, and chef removed 4, who will have the move? Chef will only have. So if I plus 2, 2 are removed, that is these two, right? These two will be removed. So here chef will have the move, chef will have the move, chef will have the move. And same thing is true for Shafina also. If Shafina is currently having the move, if only one line is removed, chef will have it. Otherwise, for these three, Shafina will still have the move. So the
Can you
so
explain the whole idea again?
yes. Let's say these are the lines. X of I is if everything before I is removed, and right now on the ith move, on this move, like on the chef is having control, and the first line which is not removed is the ith line, and y of I is everything before ith line is removed. Right now Shafina is having the control, and the first line which is not removed is I. Now if this is the case, so chef can remove 1, 2, 3, and 4. Same way Shafina can do the same. If chef removes 1, the control will shift to Shafina, right? So one thing is clear, y of I plus 1 is equals to like all these will get added, x of I, right? Because right now chef was in control. Chef removed 1 line. For the next line, Shafina is on control, right? Otherwise, x of I plus 2, x of I plus 3, and x of I plus 4. Like these are basically these. I plus 2, this thing. If chef removed both of these, or chef removed these 3, or chef removed these 4. So if 2, 3, 4 are removed, number of lines are removed, chef will still be in control. So for this, it's x of I only. Is it clear? Now, what is x of I? X of I is nothing but if at the ith line, the first line which is not removed is I, and x means that chef is in control. Y means that Shafina is in control. Is it clear?
Yeah, kind of.
And similar to this, we can write x of I plus 1, like chef is in control, plus equals to y of I, if only 1 was removed. Otherwise, if 1, 2, 3 are removed, then y of I plus 1, like I plus 2, I plus 3, and I plus 4. For all of these, you need to add yi. Like this is when Shafina will remove 2, this is when Shafina will remove 3, this is when Shafina will remove 4. So for all of these, number of waves that you could have ended here are added to these also. And if Shafina only removes 1, then number of ways to end here is added to this. Why? For the next line, control is with chef. So xi is the number of ways such that how many number of ways there are such that all these lines before I are removed, and right now the control is like the player who has to make the move is chef, and everything before I is removed. And there is a fresh move that needs to be made, and chef is the one who will make the move. And Y is for Shafina. Is it clear? Okay.
Yes, yes. It's
Okay.
kind of like push DP thing.
Yes. So now let's say this is the L. So what can be the answer? See, chef wants to win, right? So first the answer is x of L. Why x of L? X of L gave us that everything before L is removed, and right now chef is having a move to make. So always chef will remove four only, right? Why? Because he wants to end in a Tetris. So he'll remove these 4 and he can easily win, right? Otherwise, we can also add, like, what is the solution? Plus x of L minus 1. Why x of L minus 1? Because if everything before L minus 1, this was removed, chef could again do a Tetris and win. Similar to this, x of L minus 2 and plus x of L minus 3. This means that when everything before L minus 1, L minus 2, L minus 3, before this was removed, here chef was having a move, and how many number of ways are to have this kind of orientation? From here, chef could do a Tetris and win. So this is our answer. Once we calculate that array X, this is our answer for each and every L. Is it clear?
Yes.
Okay. There is only one thing: when L is less than 4, you'll have to like manually print those, like not manually, you'll have to write if conditions and print those. How? Like either you can do something like for when L is 3, you can do this thing, and when L is 2 and L is 1, accordingly like print these values. Otherwise, you can just find what are the values of L when L is 3, L is 2, and L is 1, and you can print those also using if else. So let me show you the implementation. So this is the implementation. See, first my n is this because this is the maximum limit. This is the modulo value. These are my two vectors, x and y. X1 is 1. Why? Because in start, chef will make a move. And for Shafina, everything is 0. Now we need to start from I equal to 1. And we'll go up till n and I plus plus. So every time when chef is at xi and chef makes a move by clearing 2 lines, 3 lines, or 4 lines, the control will be at chef only. So x of I plus 2, I plus 3, I plus 4. For all of these, I'm adding xi. For y, also Shefina has also the same logic, but when x makes, like chef makes a move of removing only one line, at the next line, Shefina will have the control. Same thing here. Now, when we take L as input, just check if L is 1 or L is 2, the answer is 1. When L is 3, answer is this thing. You can also like make some combination of these and print here, but this is straightforward, like for 1, 2, and 3. Otherwise, if L is 4 or more than it, we can use this thing, x of L minus 1, x of L minus 2, and x of L minus 3, and we can print it. So hopefully this is clear, right?
Yes, yes, clear.
Okay, so let's go to the next problem. So next problem is this. In this problem, we are given that Tom and Jerry have B boxes numbered from 1 to B, and each box initially contains M cheese balls and N chicken bones. Now they perform the following process for each I from 1 to B minus 1 in order. Choose I random items from the ith box and transfer them to I plus 1. Every subset I of I items is equally likely to be chosen. Now we are given integers B, M, N, and K, and we have to find at the end of the process what is the expected number of cheese balls in the kth box. Now you might like get confused with this. What is this expected value? This is nothing but like how many balls, like if you are aware of probability, so how many balls will probably be in the box. So this can be a decimal also, like a floating point number. So this problem at start seems to be very difficult. Like it seems like it is very complicated because let's say these are the boxes and each box is having M cheese balls and M chicken bones, right? Yep. So M and N. M and N. So first, let me explain what is actually happening here. So first, from here to here, we'll have I ball shifted. So that is one ball. From here to here, like from first box to second box, we'll have one ball shifted. It can be any ball. Like I'm saying ball. So let's do one thing. Let's say, okay, let's not change the terminology.
You can take M as white balls and N as black ball.
It will be easier for me. Otherwise, saying cheese balls and chicken bones will be difficult.
Yeah, sure.
Let's say this is blue balls and these are red balls. Blue and red. Okay. Blue M balls and red N balls. And finally, we have to find at the kth box what is the expected number of blue balls. Now, first, we'll have to shift one ball from first box to second box. It can be any ball. Then we have to shift two balls from this box to this box. It can be any ball. Finally, if this is the kth box, we have to find the expected number of blue balls here. Now, if we try to go like this and try to write it, we'll see like, okay, we might get an intuition that this is very complicated. Like, because this thing is clear, okay, after one iteration, after from one box, either it can be M minus 1 blue balls, N red balls, or M blue balls and N minus 1 red balls, right? These two are the only scenarios possible. But this leaves us with, after first operation, in the second box, either it will be M plus 1 blue balls, N red balls, or M blue balls and N plus 1 red balls. Then after this, we'll have to remove two balls. So if this was the scenario, removing two balls would have ended up in three cases. Either we could have gone from M plus 1 to M minus 2, and then M minus 1, N minus 1, like it would have ended in four cases: m n minus 2 or m n minus 3, right? M plus 1 n minus 3, right? These are the four cases we could have ended up. Okay, I'm removing two balls, right? I have removed how many balls? Three balls. I should have removed only two balls. Just give me a second, I'll write it again. So removing two balls have three cases: m plus m minus 1, n, m n minus 1, and m plus 1 n minus 1, right? These are the further three cases that can be in the second box. And for this also, I can get the three cases. Do I need to write those? Like, let me write it down. Like I'm removing two balls, right? So if we keep doing this, and like the probability is nothing but the number of, like what is the probability, like what is the expected number of balls in the second box? It is nothing but these are the blue balls, right? So blue balls, just add all of these. And what is the expected value? Expected value is nothing but just find the average of these. So m minus 1 plus m plus 1 plus m minus 2 plus m minus 1 plus m. So just divide this by 1, 2, 3, 4, 5, 6. This is your expected in second box. But we cannot do this. The only observation that is very important for this problem is that, see, at the start, each and every box is having the ratio m raised to n. Blue balls raised to red balls. Now, if each and every ball is equally likely to be removed, after removing I random balls, how will this ratio change? This ratio cannot change. If blue balls are more, they are more likely to be removed. If red balls are more, they are more likely to be removed. So this ratio won't change. Is anyone having any doubt in this? How can the ratio change, right? If there are 10 blue balls and 100 red balls, the probability that the blue ball will be removed is 10 by 100. 10 by, like, with respect to, like, what is the chances of removing this ball, like, other than this ball? Like, this ball is, like, red ball is 10 times more likely to be removed because its number is more. So that's why if each and every ball is having same probability, the problem, say, like, same probability of getting removed, the ratio won't change, blue by red. Is it clear? Because if this ratio changed after something, like, don't worry about the actual number of balls. If you find how many balls there are, then it might get, like, you might get different number. But if you're strictly looking at the numbers, like, after some point, red balls might come at like 3.367. This won't make any, like, this doesn't make any sense, because how can you have a ball at 0.367? But if you just look at the numbers, if each and every ball is equally likely to be removed, don't follow, like, if in your mind you'll follow one of these iterations, like, okay, I removed red from it. Don't do like this. The thing is that each and every ball is equally likely to be removed. So then this ratio won't change, because if this ratio changed, let's say earlier b by r was 1.5 and later it became 1. So this means you have removed more blue balls than you have removed red balls. Is it making sense? Otherwise the ratio will remain same. Like, even like if blue balls are 1.5 times more than red, you will remove them in that order only. Like, you will remove 1.5 more times ball. Like, what will happen if you initially there are 15 blue balls and 10 red balls? So for each one ball that red is removed, 1.5 blue balls will be removed. But eventually this ratio won't change. That is 1.5. Is it clear? Yes, no.
Yes, kind of.
So now the thing is, if we look at this from here to here, what is the expected number of balls that will go, like blue balls that will go from here to here? It is nothing but how many balls, like what is the probability of choosing up these balls? It is nothing but m plus n. So number of blue balls divided by total number of balls. So this is the number of balls, like, because you just have to do this once. So number of balls that will go from here to here is this much. 1 times this ratio into 1. The number of balls that will go from here to here is m divided by m plus n into 2, because you'll do the same thing twice. At any random I, the number of balls that will, blue balls that will go from this to this is, the ratio will always remain same. So this thing into I, right? And how many balls are coming to this? It is always how many number of balls that came to this is m divided by m plus n into I minus 1. So this is valid for each of the boxes. So how many balls, effectively, how many balls came or left with the box, like to any of the ith box. So for each of the first b minus 1 boxes, like these boxes, you will see that exactly m divided by m plus n balls left the box. Blue balls left the box. And where did all of these balls ended up? At the last. Why? Because at the last, I minus 1, like let me write this, this thing, b minus 1, this will be b minus 1, because this is the size of the number of boxes is b minus 1. These ball entered this box, but they never left. So for this thing, the number of balls is m were originally plus this is the ratio, let me call it r, into b minus 1. For all the other boxes, that is the first of these boxes, our answer is m minus ratio. Ratio is nothing but this much. These much balls left. So this is the expected number of balls in the first b minus 1 boxes, and this is the expected number of balls in the last box. For any ith box, these many balls are leaving and these many balls are entering I minus 1. But at the last box, balls only entered, never left, blue balls. Is it clear?
Yes, yes.
So let me show you the implementation.
Can you just explain the last one?
Yes, yes, yes.
Like it was actually clear that m upon m plus n into I balls, I minus 1 balls will be kind of removed from first I minus 1 boxes.
Yes.
But
But
what about the last
last
box?
box. The last box, actually, if these balls were removed, where did they end up? They ended up in the last box. So you can either just directly add m plus n into from all of these I minus 1 boxes, these many balls were removed. Either you can do it like this, or you can also look at it like this. At the ith box, let's see. If this is, let's say, ith box, how many balls are entering this box? M upon m plus n into I minus 1, right? From here. This is I minus 1. And how many balls are leaving this box? M, this is entering. And how many balls are leaving? M plus n into I, right? Expected number of blue balls that are entering, expected number of blue balls that are leaving. So for this box, only the balls are entering. So if this is the bth last box, this is b minus 1. So just remove this and write b minus 1. But the balls never left. So this is 0. So you just have to add in the last box this much. Also, you can look at like this, like for these first boxes, exactly this much balls left, m upon m plus n. So where did they end up for all of these b minus 1 boxes? They ended up in the last box. Or you can look at like this also. Is it clear?
Yeah,
Yes.
I got it. It's clear now.
So the solution is, first take b, m, n, and k as input. If b is 1, simply print m. The number of balls won't change. Otherwise, first find the ratio. This is just to make sure that I'm printing the right number of decimals. And if k is equals to b, that is, I have the last box, I'm printing m plus r ratio into k minus 1. This can be b minus 1 also. B and k are same. Otherwise, my answer is m minus r, expected number of blue balls. So the only thing in this problem was to notice that the ratio won't change if each and every ball is equally likely to be moved to next cell, next box. So is it clear?
Yeah, it's clear.
Okay.
Now,
So
what topic does this question requires? Like the combinatorics or something like?
Yeah,
Probability.
kind of combinatories, but more like probability.
Got
Like
it.
there's nothing much like it's a part of combinatories only, but more like probability.
Got it.
So that's it. And thanks for joining.
Thank
Bye
you.
bye.